Look at any military boot camp, physical education class, or martial arts dojo in the world, and you will see the exact same movement. The push-up is the universal standard for measuring physical endurance and discipline. From the outside, it looks like a basic chest press, but underneath the skin, it requires a high-tension, full-body isometric plank. As you lower yourself to the ground, your pectoralis major, the thick, fan-shaped muscle of the chest, and the triceps brachii on the back of your arms act as the primary engines, contracting to push your mass back up. Those engines cannot function without a rigid chassis. The transverse abdominis, a deep core muscle that wraps around your spine, along with your glutes and serratus anterior, have to lock your pelvis and spine into a neutral position. They fight a constant battle against the downward pull of gravity. This creates a unique mechanical problem. If your goal is to build strength, overcome a plateau, or target a specific weakness, how do you progress when your resistance is permanently fixed to your own unchangeable body weight? You don't actually need to add external iron plates. Instead, you have to treat the human body as a machine and manipulate the specific biomechanical variables of the movement. The first variable you can adjust is your base, which is dictated entirely by how wide you place your hands relative to your shoulders. Moving your hands close together into a diamond shape forces your elbows to migrate tightly against your sides. This places the triceps at a severe mechanical disadvantage. Because the chest muscles are in a poor position to help, the triceps have to take on the majority of the load, generating over 100% of their maximum voluntary contraction to complete the rep. Widening your grip well past your shoulders forces your elbows to flare outward laterally. This stretches the pectoralis major, improving its length-tension relationship. The physical burden shifts away from the arms and lands directly on the chest and the anterior deltoids in the front of your shoulders. This diagram shows the specific zones of the human palm where physical pressure is distributed during these movements. The hand is divided into 5 specific areas, spanning from the base of the thumb over to the pinky, with the lunate right in the center. Clinical data reveals that adopting a wide grip drives heavy pressure directly into the lunate area, the inner base of the palm. Sliding the hands into a narrow grip forces the weight to the outside edge, into the hypothenar area. Adjusting your base allows you to route physical pressure away from existing joint or tendon pain, depending entirely on your unique anatomy. The second variable is the lever. In physics terms, a human performing a push-up is operating as a Class II lever system, with the toes acting as the fulcrum or the pivot point. When you perform a standard push-up flat on the floor, gravity dictates that you have to press anywhere from 64 to 75% of your total body mass. Placing your hands on an elevated box mathematically shortens the lever arm relative to your center of mass. This physical adjustment drops the required pushing force down to just 41% of your body weight. Elevating your feet creates a decline angle. This shifts the gravitational burden directly over the upper chest and shoulders. The lever mechanics now work against you, acting as an intense overload mechanism that forces you to push up to 74% of your total mass. By mastering the math behind this lever system, you can scale your resistance training from absolute beginner to elite athlete without ever touching a dumbbell. The final variable is the surface itself. Watch what happens to the mechanics of the body when the ground beneath it refuses to stay still. This is the exact concept behind suspension training. Instead of planting your palms against a solid floor, your hands are placed into freely moving straps. Removing stability triggers an immediate response in the central nervous system. Because the hands can independently swing in multiple directions, your muscles have to fire aggressively and continuously just to keep the joints aligned and prevent the structure from collapsing. These bar charts measure that exact neurological response in the form of electrical muscle activity. The data demonstrates statistically significant surges in both anterior deltoid and triceps brachii activation during the suspended push-up, compared to the traditional floor version. Introducing instability transforms a standard pressing motion into a high-frequency stabilization task, building deep functional stabilizers that traditional machine-based weightlifting often misses entirely. The push-up functions as a highly customizable physiological operating system. You can deliberately engineer your physical performance by combining these variables. You might utilize a narrow grip to target the triceps, elevate your feet to increase gravitational load, and use an unstable surface to force deep joint stabilization. Achieving progressive overload and pushing past physical plateaus does not mandate a room full of expensive isolation machines. Mastering the geometry of your base, the physics of your lever, and the neurology of stability, you can scale bodyweight training into a tool